Hello, Mr. Avery, Mr. Ryan, right?
Yeah.
Okay, so we're given a positive integer, and with one operation, you can add or subtract a power of 2. And we want to minimize the number of steps to reduce the number to 0. Given example like 7, right? So we only need 2 steps. 7 plus 1, because 1 is 2 to the power of 0, and a minus a. A is 2 to the power of 3, so that needs 2 steps. Of course, you can do 7 minus 4 minus 2 and minus 1. That needs the 3 steps, right? So we talk about this finding the nearest power of 2. One greedy approach, for example, like if you put the number here 7 and the next closest power of 2 is 8, the previous closest power of 2 is 4. Okay, so because this is shorter, so we go this way, right? So we always look for the shortest power of 2. This is greedy, okay? But we need to prove this is correct. How do you prove that choosing this closest to gives the optimum? There are multiple power of 2, right? The next power of 2 is 16. Another power of 2 before 4 is 2, right? If we choose the brute force, we can also jump 16 as well, or jump to 2 as well. From that point, it also takes one more step. But why we choose the closest power 2?
It's much more easier.
It's easier, yes. From this point of view, we can do this programming using top-down dynamic programming because there are only 2 closest to, right? There are only 2 closest to. You can check the left, check the right. Look, remember this tree? Fn minus 2 to the power of a, 2 to the power of a plus 1 minus n, right? It's a binary tree, and in order to calculate Fn, we need two values. And in order to calculate this, we need another 2 values. So each tree has 2 kids, maximum 2 kids. This is binary tree, and we can implement this using recursion, which we can put a cache, add cache. This is top-down dynamic programming. So each Fn value is calculated exactly once. So this one, we pick 2. This is still greedy. Brute force is a little bit greedy. As I said, it's not 100% brute force, right? Brute force is that with this n, right? With this n, and then what's next? What's next? You need to move left and right. There are multiple choice, right? But that's impossible. I mean, it's not feasible to implement this brute force, because if you imagine it's a search tree, and instead of 2 kids, it could have multiple kids. And to fully explore this whole search tree, it's going to take time. It's not very performance efficient, right? So we go for this only 2 branch. But we still need to prove it. Without proving it, we don't know. For example, like this one. If we are at 7, right? We jump to 16. That's going to take another 1 step. We jump to 8. That's going to take another 1 step, right?
Yeah, because the distance between the 2 power of 2 must be another power of 2. So between 8 and 16 is 8.
Mm-hmm.
So you have to add 8 to what? So 7 to 8. You have to add that to 8 plus 16.
Excellent.
8,
yes, yeah, excellent.
8 and 16.
Yeah, that's true.
So that
because
means it's just adding more moves.
well done. Very excellent. Yes. So from 7 to 8, right? This is, and you're saying that from 8 to 16, this is power 2, right? This is one more step, right? All right. Yeah. So this must be optimal. So it's sufficient to look at this left and right. Okay. So that's the first approach we talked about in the first day, right? Recursion. If n equals 0, obviously we return 0. We don't need to do anything. If n and n minus 1, if it's power of 2, then we return 1 step. Otherwise, we check these 2 branches, right? On the second day, on the last lesson, we also talked about we check for this smallest. We don't need to check both, right? So instead of searching for 2 branches, we only go for 1. So this is kind of like a linked list, right? Every time we just we just pick a direction and go, right? This is kind of like binary search. So this further reduces the term complexity. Okay, but we also need to prove this, right? We need to prove this. But today, okay, we're going to study this problem using mathematics. In order to solve this puzzle, computer science programming, algorithm, mathematics sometimes connected. It's very related, right? So mathematics helps you to do this programming. So with the mathematics, then we can design a much better, efficient algorithm. This Fn. Fn is the minimum number of steps to bring n to 0. Okay? So n is an integer, right? N is an integer. So it's a sum of the power of 2, am I right? So we want to bring down n to 0 by adding or subtracting a power of 2, alright?
Yes.
Okay, so I can write it this way, right? N equals k0, 2 to the power of 0, plus k1, 2 to the power of 1, plus k2, 2 to the power of 2, plus k3, 2 to the power of 3, etc. to km, okay? Km 2 to the power of m. Am I right? There could be multiple items. For example, 7. 7, I can write it this way. 7 equals 1 plus 2 plus 4, right? Also, it can equal a minus 1, right? Minus 1, 8, okay? Minus 1 plus 8. So look at this. 7 equals 1 plus 2 plus 4 equals 2 to the power of 0. K0 will be 1, right? 1 times 2 to the power of 0 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 2. Okay, plus, all the rest, the k will be 0, right? Plus 0 times something, okay. Right, am I right? This is k. Ki, okay? K0, this is K0, this is K1, this is K2, okay? Make sense? Yeah. And this one, minus 1, right? Minus 1 times 2 to the power of 0, plus 1 times 2 to the power of 3, right? And 0 times 2 to the power of 1 plus 0 times 2 to the power of 2. It doesn't matter because we don't have 4 and 2, so we put a 0. This is K2, this is K3, this is K0, this is K... Actually, this is K3, this is K4, okay? K4. We can rewrite this. This is sum. Remember, this is simple. N equals I equals 0 to m, right? This whole thing can be written as sum I from 0 to m. Ki times 2 to the power of I. Am I right? Look, this whole thing in mathematics. Does it make sense? Look, Ki times 2 to the power of I from 0 to m. So what's the value of Ki? Can I ask you, what's the value of Ki? If you look at this, what's the value of Ki?
1 minus 1, that's all I see.
How about
0?
Yeah, 3 values. Yes, Ki only 3 values. Minus 1, 0, 1. Okay. Minus 1. This is minus 1. Right? 0, you got nothing, right? And 1, you plus it. The cost, the number of steps is equals to sum I equals 0 to m. And then we want to, the sum is this one, right? This is the step, right? If minus 1 and 1 step. If it's 0, we ignore it, right? If it's not 0, then it involves 1 step. So it's absolute value Ki. Okay? Absolute value Ki. Okay, so before we started this problem, we have to realize that the order of the subtraction and addition does not matter, right? For example, plus a minus 1 is the same as minus 1 plus a. Okay? So the order does not matter. Another thing is that we cannot have any two additions of same power of 2. Plus 4 and then plus 4 again, right? Yeah, because this is 2 steps, but actually you can merge it to a, which is power of 2. Am I right? Yes? Because 2 to the power of I plus 2 to the power of I equals 2 times 2 to the power of I equals 2 to the power of I plus 1, right? So this is 2 operation. Now we just need 1. Similarly, we cannot have 2 subtraction of the same power. We cannot say minus 4 because this would turn into minus 8, which is just 1 step. And we cannot have adding 4 and subtracting 4 because it just becomes 0. It doesn't make sense if you just plus 4 and minus 4.
What if you got 0?
0 step, okay? This is what I'm saying. So, okay, this is the very obvious. Let's move on. If x is even. So, if x is even number, right? If x is even number, then we can say x equals 2 times x.
Apostrophe.
So, x is an even number. So, the k0 must be, if x is an even number, the k0 must be
0.
That's right, because if it's even number, k0 is 0, okay? So k0 is 0, then we can rewrite this. We can divide it by 2 on both sides. So x divided by 2, this will be equals x apostrophe, right? Apostrophe. Okay, and this side divided by 2 is I equals Because k0 is 0, so we ignore that, right? So k equals 1 to m, it doesn't change. Ki times 2 to the power of I minus 1, right? Because we divide it by 2. We can make it to 0, then we can keep rewriting it equals I equals 1, right? We can make it 0, so I equals 0 to m minus 1. K I 0, then I will be ki plus 1 to I, 2 to the power of I. Okay, let me repeat, okay? If x is an even number, right, then we can write it as 2 times of x,
Apostrophe.
x as apostrophe. Okay, and then we divide it.
We even learned about apostrophe in year 1.
Okay, so we divide it by 2 on both sides. The left side is x apostrophe. The right side we divide it by 2 because k0 is 0, so we get rid of this item, divide it by 2. So basically this thing divided by 2. Each item will be I minus 1, right? I minus 1. And ki. I is from 1 to m, right? And now we're writing it using this way. This one is mapping, have 1 and 1 mapping. So fx apostrophe, right? This is half of it.
Apostrophe.
Apostrophe. This is
Apostrophe.
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 Can I just say x dash?
No, you have to say apostrophe.
Apostrophe. Okay.
Apostrophe.
I can't pronounce this. Okay. Anyway.
You're not trying. Apostrophe.
Okay. You know what? I'm going to rename this to y. Okay. Okay. Yeah. Happy? Yeah. Okay. Y is half of the x. Actually, it's even number. Okay. So
Apostrophe.
y. Okay. Okay.
Sounds like you said Y. W-H-Y.
Y.
Apostrophe.
Fy and fx is 1 and 1 mapping. 1 and 1 mapping. Fx must be the optimal as the same thing as fy. Because if not, then we can reduce the x, right? In this way, right? Am I right? Fx equals f2x. Okay? Yeah? Makes sense. I'll give an example. Like fa, is it the same thing as f16? Am I right? Do you get it? We want to prove this. Fx is equals f equals 2x for any given x, not just the power of 2. Okay? So we just prove it because this fy, y is the half of x, is 1 and 1 mapping to this because what we just did, we divided by 2 on both sides and then we write this index. Then it's basically the same thing. Okay? Okay. So if x is even number, then we have this, right? Okay, so it's actually f2x equals fx. Okay, this is even number. For the odd number, what's the value of k0? If x is odd number, what's the value of k0?
Apostrophe.
If x is odd number, what kind of value can we have for k0? Look, remember this is 1, right? So what kind of value for k0? K0, k1, k2, k3, these are the weights. There are only 3 values for each item, which is minus 1, 0, and 1. For the even number, is 0 because the first item is 1, right? There is no 1 in the even number. But for odd numbers, what are the possibilities?
Minus 1 and 1.
There are 2 possibilities, yes. K0 could be 1 and K0 could be minus 1, right? Because this is the item of 1. If it's 1, right? If it's 1, we can...
19.
If it's 1, then we can subtract 1. If it's 1, we can subtract 1 on both sides. If it's minus 1, we can add 1 on both sides. Okay, if it's 1, let's say if k0 is 1, then this is 1, right? So we minus 1 on both sides. We minus 1 on both sides, so this item is gone. Both sides would be minus 1 and divided by 2, okay? Minus 1 and divided by 2, minus 1 and divided by 2. We have this similar form of these. When x is an odd number, we must search the half version of it. And if k0 is minus 1, it's the same. There are 2 cases, and both will be converted to this kind of form. Why do we need to care this form? Because this is the same thing to the original. It means that it's a 1-to-1 mapping. So if we want to find out the minimum of this, the value of this, we must find out these 2 cases, which is that f2x equals 2x plus 1. This is odd number equals fx and fx plus 1. Okay, fx and f plus 1, the minimum version of it, plus 1. Okay, plus 1. Why do we need plus 1? This is
minus 1 plus 1 equals 0.
Yeah, I was just saying that +1, right? Here, +1. We need to get rid of these items. We need to get rid of this item. This is the singular one. Okay, so it means that this is the step for that. Okay. Okay, so with these two equations, right? With these two equations, this is the case for the odd number, and this is the case for the even number, right? So we can reduce any given x to half of it. So each time we call this fx, we'll be able to reduce this x to fx divided by 2, roughly, right? X divided by 2. Okay, look, 2x becomes x. 2x plus 1 becomes fx, and fx plus 1, okay? So every time we should be able to reduce this, then we can implement the recursion and using the cache top-down dynamic programming. This is the mathematical proof of that. Okay, I'm going to give a quick quiz.
Aww. Quizzes are not fun.
Fx
Apostrophe.
plus 1 smaller or equal than fx plus 1 bigger than equal than fx minus 1. Okay, so can you prove this? Can you prove this?
Fx plus 1 is small.
Okay, let's look at this.
I'm not finished yet.
Okay, so can you?
It's smaller than fx plus 1 because fx plus 1 is basically x. Yeah, because if you plus 1, it's obviously bigger than if you minus 1.
No? Okay, let's look at this. Let's look at this first. Why this is correct. This is x, right? This is x plus 1. So we want to transform this x plus 1. So one possibility is from x to x plus 1. How many steps? If we want to jump from x to x plus 1 step, yes. So that's why, look, if you want to reach fx plus 1, you can do it from fx, and then you need to plus 1, right? It's smaller or equal, right? And similarly here, how do we interpret this?
2 minus 1 is 1 and 2 add 1 is 3, and so that's basically... Yeah, because if you add 1, it's obviously going to be bigger, then you subtract 1. Because 2 minus 1 is 1.
Okay, so can we look at this like... can we look at this, this is still the same, right? From x plus 1 to x.
Yeah, right.
Right? So this is the other way around, right? If we want to transform from x plus 1 to x, so x plus 1 to x needs one more step, right? So it's fx plus 1, and that would come to fx, right? So it's bigger or equal than fx. Okay, so look, if this one moves to this side, it will be minus 1, right? Yeah? Alright, if you move this to the other side, you'll be changing the sign. Okay, make sense? So this way, we just put it here, it will become plus 1. So fx, we want to transform from x plus 1 to x. So if we want to transform x plus 1 to x, we need one more step. So that's why fx is smaller than fx plus 1. Plus 1, right? And then this one move to the left, it will be minus 1. Okay. And we also can use the induction, right? To prove this using those formulas, as I said earlier. Okay.
Begin dot, yeah.
Okay, let me write this in Python and that's it. Okay. This is today's solution. Define fx cache.
29.
Look. If x equal 0, return. If x equals 0, return 0. If x and x minus 1 equal 0, if it's a power of 2, return
Apostrophe.
1. Okay, now we need to find the half of it. Okay, x apostrophe. Right?
Apostrophe.
Okay, let's
apostrophe.
If x and 1 equal 0, if it's an odd number, right? If it's an odd number, then we simply return fx divided by 2, half of it, right?
It's apostrophe. True.
Okay.
Apostrophe.
Okay, we know it, right? If it's even number. If it's an odd number, then half of it, right? Half of it. Apostrophe x divided by 2. Then return minimum of x apostrophe and f apostrophe plus 1. Okay, that's it. Look, this is the equation today. Do you get it? So we want to calculate fx. We can always reduce it to half. Look, this is half. This is half, right? This is half. So look at f 120. We need to go to f 60. F 60 we need to go to f 30 because it's the same thing, right? We just prove this. F 30 we can get the f 15. F 15 we need to calculate f 7 and f 8. Okay? F 8 is the same as f 4. F 4 is the same as actually f 8 we can finish here, which is return 1. F 7, right? F 7 equals f 3 and f 4, right? F 4 we also get it as well. F 3 we can get to f 1 and
F2.
And f 2, yes.
Yeah!
Okay, f 2 1.
Ow!
The time complexity and space complexity is all log n, right? Because we're reducing half. Okay. What have you learned today? That's it.
Power of 2 again,
Yeah.
but using maths.
Okay, so what have you learned? What's your takeaway? You know?
Dad can't pronounce apostrophe.
Yeah.
Okay. So why we spend so much time doing this math today? Because if you want to use this equation, right? We need to prove that it's correct. Okay.
Look, it's red.
Okay. We need to prove it's correct. Okay. There's some parts missing because it's a lot of work on the whiteboard, so it's quite similar. I mean, you can do it yourself. Okay. That's it for today. Bye bye. Bye bye.